Winding down with the trig unit. We've only got a couple days left, but got another day of sinusoidal modeling today. I'm starting with the homework. Homework looked really good last night. I'm really pleased with the job everyone's doing. I did have a couple of questions on the back, number 3. This one, the calculator one. On a standard summer day in upstate New York, the temperature outside can be modeled using this equation. So they give us the outside temperature equation, where T represents the number of hours since the peak temperature of the day. A says sketch a graph for this function on the axes below for one day. Okay, well, I would assume that most of you know to go to y equals and plug in this equation. So it's 11 cosine of pi over 12 x, close the parentheses, plus 71. A couple of you talked about having straight lines. That's because your mode's wrong. Make sure your mode is in radians because we got pi's involved, and anytime you do a graph, it should be in radian mode. And then make sure your window's set up right. Now the graph gives you the window. You're seeing from 0 to 24. So x min is 0, x max is 24. Doesn't really matter what the scale is. And for the y's, you can go from 0 to 90, but they kind of got this break in the graph. Really all we care about is 50 to 90. So I would go 50 to 90. And then just hit graph. And again, you don't have to really worry about the window because they essentially gave you the window. Okay, so that's where you get your equation from. And notice it's not going, if our max is 90, it's not going all the way up to 90. So this looks something like this. Oops. All right, rough sketch. Then part B says for 0 to 24, graphically determine all points in time when the outside temperature is equal to 75, found the nearest tenth. Okay, so now I just put y2 equal to 75. Throw the graph in there. You can see I've got 2 intersection points. So second calc intersect, first curve, second curve, guess. And you get 19.4 for one of them. So let me just draw this in here. We've got this point here is 19.4. And then do the same thing for the other one. Second calc, intersect, first curve, second curve. So we want to time we want to get all the way over to this one. So when I guess, I got to arrow over to that one. .6. So the points in time when the temperature is equal to 75 degrees, about 4.6. What is this? Hours since the peak temperature. So 4.6 hours after the peak and about 19.4 hours after the peak. All right, so that's all you had to do for that one. I'll calculate it work. All right, let's go to warm up next. Now this warm up's a little weird, so let's just do it together. Part A, I think you could do totally fine. Sketch a graph of y equals sine of x between 0 and 2 pi. All right, so we got nothing crazy going on. We're just going to set up some axes. This is obviously 0, pi over 2, pi, 3 pi over 2, 2 pi. So this is the normal cycle of sine, the first cycle of sine that you ever saw. It went up to 1, it went down to -1. And where does sine start? It starts at 0, the midline. So it goes 0, then it goes up first to 1, back to 0, -1, and it ends at 0. Okay, so there's sine between 0 and 2 pi. Now I want to sketch a graph of y equals cosine of x, also over 0 to 2 pi. So I can set it up the same way, 0, pi over 2, pi, 3 pi over 2, and 2 pi. But I'm not just sketching cosine, I'm sketching cosine of x minus pi over 2. What's this minus pi over 2 doing to the graph? It's a phase shift. It's going right pi over 2. So if you wanted to think about it, that means our phase shift is pi over 2. So in order to graph that, I told you wouldn't have to graph this much this year, and that's true, you won't. Here's the regular cosine curve up here first. So cosine generally starts above the midline, then it goes all the way down to -1, then it ends up back above the midline. So what we're going to do is we're going to have to shift everything right pi over 2. Okay, so this point's at 1 up here when x is 0. I'm going to shift that right pi over 2. We're going to plot it at 1 right here. This point is 0 at pi over 2, shifts right, so now it's going to be at pi. This -1 shifts right pi over 2, so now it's at 3 pi over 2. This 0 shifts right pi over 2, now it's at 2 pi. Now what point would be at 0 up here? Well, it's whatever point was at -pi over 2. And if you keep going with the cosine graph, it would have been 0. So look what happens when I shift cosine pi over 2 to the right. What do we got? We've got sine. So my purpose of showing you this was that for conclusion, cosine is just a shift pi over 2 to the right of sine. So it's really the same graph, just shifted left or right a little bit. In this case, right. What that means is anytime we make an equation in terms of sine, I could make an equation in terms of cosine by just adding some sort of phase shift. Same thing with the other way. If I have a graph in terms of cosine and you'd rather it be in terms of sine, you can just add a phase shift to it and you'll get the other trig function. So you're going to see that a little bit in the notes today. Random fact of the day, the smallest county in America is New York County, also known as Manhattan. You know that. Okay. Let's go to today's notes. So we're doing more sinusoidal modeling. It'll be some of the stuff you saw yesterday, but now you've got phase shifts in there, and we're also going to talk about regressions. All right, so the first thing we saw is what I just showed you. Since sine and cosine differ only by a phase shift, it's possible to use either sine or cosine when finding models of periodic data. However, it's sometimes necessary to use phase shifts in order to do that. Let's say I've got Chicago's monthly average temperatures. So month 1 would be January, February, all the way to December. Average temperatures over the course of a year would be periodic because over the next year we'd expect them to be about the same. Okay, first step says to graph the data on the axes provided. So just we're going to graph these the best we can on here. So 1 is 23.8. So something like that. 2 is 27.7. We'll go there. 3 is 37.9. There. 4 is 48.9. 5 is 59.9. Almost 60. 6 is 68.9. Probably right about there. 7 is 74. Wish it was 74 degrees today. 8 is 72.4, so July is the hottest month, it looks like. 9 is 64.6. 10 is 52.5. 11 is 40.3. And 12 is 27.7. Okay. So if you were connecting the dots here, what would you say it looks like? Well, it definitely appears roughly like a sinusoidal graph, sine or cosine. Would you say it looks more like sine or more like cosine? Well, it starts below the midline, because the midline would be up here somewhere. So it can't be sine, it'd be cosine. So from this graph, I would say, oops, sorry, I just messed up the whole graph. What was the first one? 23.8, about there. Okay. I would say this appears roughly sinusoidal. I'm Remember, sinusoidal just means it's a sine or a cosine graph. Specifically, I would say it looks more like negative cosine. But notice down here it says find a model for the set using a sine function. So it's not letting me choose cosine of this form. All right, so most of this is what we did yesterday. So if I want to find the amplitude, that A, how do I do it? That's max minus min divided by 2. So we've got to use our data. What's the maximum? I said that was July, right? And what's the minimum? Looks like January. Okay, so that would be 74 minus 23.8, all divided by 2. Let's do that in the calculator. 74 minus 23.8, hit enter before you divide by 2, and we get 25.1. Okay, so that's our A value. What's B? Well, B, we got to use period equal to 2 pi over B. But what's the period? Well, think about what one cycle is. The course of a year is one cycle because the next year is going to repeat. So it's 1 year. And if we're talking in terms of months, one cycle is going to happen every 12 months, right? So we're going to say 12 equals 2 pi over b. We're going to cross multiply. We'll get 12b equals 2 pi. So divide by 12. And you get b equals pi over 6. Okay, we'll come back to C in a second because that's the new part today. But yesterday we could have found that midline, D, by doing max plus min divided by 2. So we already said the max was 74. This time plus the min of 23.8 divided by 2. And I end up with 74 plus 23.8 divided by 2, 48.9. Okay, so I've got pretty much everything I need except this phase shift. So let's talk about that for a second. So C is the phase shift. Now they want us to think of the sine graph. They want us to use the sine graph. And just like the warm-up, where does the sine graph start? It starts on the midline at 0. So what you should see from this is that sine cycle starts at midline. So what value of cosine or what value of this data is closest to our midline, which is 48.9. All right, so let me talk about that for a second. If I want the cycle to start on the midline, well, the midline in my graph up here, we just found the midline was 48.9. Okay, so if I said this is the start of my cycle right here, then I go up first, I'm coming back down, I eventually come back up again. There's your sine graph right here, right? So if I want to do this in terms of a sine graph, this has to be the start of my cycle, which means that sine graph was shifted to the right a distance of 4. So when I said this, I know I want to start at the midline. I got to look at what value is closest to my midline. It's 48.9. I actually have my midline. That's perfect. So I had to shift this far to the right. That's our C value. So the value that's closest is t equals 4. So that means, so shift right 4. And how do I make the graph shift right 4? What would C have to be? This would have to be a negative 4. All right, so there's my equation. Y equals A is 25.1 times the sine. And notice how that's written. B is factored out front, pi over 6. Then in parentheses, it's x minus 4, double parentheses, plus the midline. Okay? Now, incidentally, that's the exact same as if you had done negative cosine. If I had said y equals negative 25.1 cosine of pi over 6x plus 48.9, that's what I would have had you done previously because this graph looks like a negative cosine. So normally I would say avoid this whole phase shift thing. If you can make your shifting start at 0 or your cycle start at 0, do that. The only time you have to use the phase shift is if they specify that you have to use a specific trig function like this one. Okay? Okay. Now it says use your graphing calculator to obtain a sine regression model for this data, rounding all coefficients to the nearest tenth. What do I normally do first if I'm doing a regression equation? Right, we do L1, L2, right? Okay, so I'm going to go back up to all the data. We're going to type this into our calculator. So I'm going to go to Stat, Edit, and then if you have stuff in here, remember, highlight it, hit Clear. So clear those both out. And we're just going to start typing in these numbers. So 23.8, 27.7, 37.9, 48.9, 59.1, 68.9, 74.0, 72.4, 64.4, or wait, 64.6, 52.5, 40.3, and 27.7. Okay, so after that, we always go to Stat, Calc, and here's all of our regressions, and we're looking for something that looks like a sine regression. So way down, and choice C is sine regression. Hit enter. Leave everything as is. Make sure it says L1 and L2, or wherever yours are. You can leave everything else kind of alone. Just hit calculate. This is invalid dimensions. What did I just do? Hang on 1 second here. Let me figure this out. Oh, I was completely stupid. That's what I did. Months should be L1. Average temperature should be L2. So don't waste your time. Let me do that real quick. I'm going to clear this out. I'm going to pause the video and put those all in, then we'll restart. All right, sorry about that. So I got everything in L1 and L2 now. So now, if I go and do that sine regression, it should calculate. There we have it. Okay, so I went to Stat, Calc, sine regression. And my equation, they tell us up here, now look, it's written slightly different in that B isn't factored out. It's bx plus c. Here the b has an extra set of parentheses. So your numbers are going to look a little different, and that's why. But you'll notice a lot of them are the same. Okay, so using all these, we want it to the nearest, what does it say? 10th. It's going to be y equals 25.2 times the sine of, nearest 10th would be 0.5x minus 2. So 0.5x minus 2, and then plus 48.9. Now look at how close this is. 25.1, 25.2. 48.9 is exactly the same. You might think these inside is totally different, but look, if I do pi over 6, let's see what b actually is. Basically 0.5, so that worked out. And if you did factor out this 0.5, meaning like if you divided 0.5 by both pieces, if I do -2 divided by 0.5, because that's what taking a GCF is, I get -4. So it's really pretty much equivalent. It's not always going to be that close. And part D says, what are the two models you created predict for the average temperature in June? So in June, what would I be plugging in for X? And June is the 6th month, so X is 6, right? So for our first model, we would have Y equals 25.1 times the sine of pi over 6 times parentheses 6 minus 4 parenthesis plus 48.9. And we just plug that straight into the calculator and see what we end up with. 25.1 times the sine of pi over 6 in parentheses 6 minus 4, you could just write 2. Make sure you do double parentheses there, plus 48.9, and I get about 70.6 degrees. Okay, and I'm going to do the same thing with my regression. 25.2 sine of 0.5 times 6 minus 2 plus 48.9. I'd expect something similar, so close to 70.6. 25.2 times the sine of 0.5 times 6 minus 2, close the parentheses, plus 48.9, and I get 70.1. Very close. Let me check one thing real quick. Stat, calc, all the way down to sine regression. Did I get that totally right? Yeah, it looks too close. That D value should be 48.7. Sorry about that. Making mistakes left and right this morning. So that was really 0.7. It isn't a huge deal, but the only reason I noticed it was because I thought this was farther off. If I go back to the home screen here, and if I enter in what I just did, and put a 0.7 there, then it's 69.9. Still close, but a little bit more off. Okay, so you can see that they're very close, and I would say the regression is actually the more reliable one because you're using all of the actual data when you created that equation, whereas we only used a few of them when we created our theoretical equation. Okay? All right, over on the back. We got another one. The table below gives the amount of daylight in hours in Chicago on several days throughout the year. So just like the temperature, there's more daylight in the summer, less daylight in the winter. Find a model using a sine function. So again, even though this would probably be a cosine function, they want us to use a sine function. So we're going to do this exactly like we did yesterday again. I'm going to find the a value by doing max minus min divided by 2. Let's scan through this. What's the max? It's right here, 15.17. And the min looks like it's 9.2. Okay, so we're going to have 15.17 minus 9.2, all divided by 2. 15.17 minus 9.2. Hit enter before you divide by 2, and you get 2.985. That's our A value. Period is how long. Now this time we're not talking about months, we're talking about days. So assuming this is cyclical every year, even though it only goes to 335, be a little smarter than that. Period is 1 year. So we're going to say 365 equals 2 pi over b. Cross multiply, we get 2 pi equals 365b divided by 365, and that's not going to reduce at all, so b is 2 pi over 365. Let's do midline, because that's easy. That's just max plus min divided by 2. So 15.17 plus 9.2 divided by 2. 15.17 plus 9.2. Hit enter before we divide by 2. And the midline is 12.185. So that's going to be D. D equals 12.185. Okay, so to find the phase shift, it's the same as a second ago. This would look like a negative cosine. We've got to shift it so that it starts at that midline. So scan through which value is closest to the midline. And there's nothing exactly 12.185 this time, but I guess this is the one that's closest to the midline. And that's a shift of 91 days to the right. So for the phase shift, 91 x equals, or t equals 91, is close to that midline of 12.185. So we want to shift right 91, which means that c value needs to be negative 91 to make that go to the right. So putting that all together, we have y equals 2.985 times the sine of b, which is 2 pi over 365, and then parentheses x minus 91 plus 12.185. Okay, so there's your equation like we did yesterday, adding the phase shift in because they asked specifically for sine instead of a negative cosine. When it says determine the sinusoidal regression, that's when I do stat calc sine regression. All right, so first I've got to go to stat, edit, and clear out everything we had from before. And let me get up to the data so that I can see what I'm typing in here. We're typing in 1, 32, 60, 91, 121, 152, 182, 213, 244, 274, 305, and 335. Okay, so there's our L1. Now we're going to go over to L2, 9.2, 10.05, 11.25, 12.72, 14.03, 15.02, 15.17, 14.4, 13.13, 11.75, 10.37, and 9.37. Okay, so I got that all in there. And now I can go to stat, calc. I know it's choice C, or you can arrow all the way down to sine regression. Let's calculate that. And we're going to round everything to the nearest hundredth this time. So y equals 3.00 times the sine of b is 0.02x and c is minus 1.31. So 0.02x minus 1.31, and then our d value on the end is 12.12. Again, if you compare that to what we made, pretty close. Amplitudes are similar. If you do 2 pi over 365, you'll get something close to 0.02. You know, if you factor this out, it comes out similar to that, and 12.185 is pretty close to 12.12. Okay, Use both of your models to predict what period of time during the year Chicago gets at least 12 hours of daylight. So 12 hours of daylight, is that an X value or a Y value? That's a Y value. So we essentially want the X value, and we want it when the Y value is 12. So we got to solve this graphically. So I got to go to Y equals, and I've got to plug in my first equation, 2.985 times the sine of 2 pi over 365. And then in parentheses, we put x minus 91, parenthesis, parenthesis, plus 12.185. And y2, I'm looking for 12 hours of sunlight, so that's going to be 12. Now we got to be smart about our window. What should x min, x max be, do you think? Well, we want over the course of the year, so go 0 to 365. And for y min, we know 9.2 is our min, so let's just say 9. And we know y max, we know our max was 15.17, so maybe go 16. And that should give you a somewhat decent graph. So hit graph. Now again, it's going to look like a negative cosine graph, but we've shifted it. So that's why it's sine. Even though it looks like negative cosine, we know we put in a sine graph. And there's y2. So I can find second calc intersect the days when there's about 12 hours of daylight. So it's at day 277. And if I do second calc intersect again, this time arrowing all the way over to the left before I hit guess, hit enter, looks like 87. So it's from day 87 to 277. Okay, so for work-wise, just show what we had. This was 87. This was 277. So there's at least 12 hours of sunlight from day 87 to day 277. We could figure out what month those were in if we wanted to. Probably March to October or something like that. All right, but that was my original equation. Now I've got to use this second regression, so I'm going to leave everything as is, but just change my first y equals to that regression equation, 3.00 sine. Remember, this one's written a little bit different. It's 0.02 x minus 1.31. There's no extra set of parentheses in there. Plus, what was the answer? 12.12. Hit graph on there. And you'll also see a negative cosine graph. This one you'll see is shifted a little bit more. And we did round those regression equations. It kind of starts a new cycle a little bit early. So because we rounded those values, this is maybe not as reliable this time. But I can still do second calc intersect. And you can see it's a little bit further off. We've got, this would be day 225 over here. If I do second calc intersect again, this time going all over to this one. And hit enter when you get there. 63. So day 63 to day 225. And this graph looked more like, started negative cosine, but the cycle just kind of restarted early. So again, this was 64, something like that. This was 225. So kind of significantly different. So from day 64 to day 225. And the reason it's significantly off, again, isn't because our calculations were so bad. It's because of our rounding. Rounding really does affect a lot. You saw it, I mean, it was a mistake that I made over here, but just making this 0.7 instead of 0.9 already threw this off about 2 degrees. So if I round like I did here, it throws it off so much that the cycle starts back up before January. All right, so just be aware of that. Regression is probably more reliable because you're using the exact data, but it becomes less reliable when you round. All right, that's all I got. So give the homework a shot and email me with questions. Good luck.